In the second half of lecture 26, I will go over a few questions and problems from the textbook that has to do with the physics of engines. I will start with question 26.1. In this question, we have three Carnot engines. One is operating between 400 and 500. Another one is operating between 500 and 600. And the third one is operating between 400 and 600. And we are asked to rank them based on the magnitude of the work that they do. Greatest first. I will write basic equations here. For a Carnot engine, efficiency is 1 minus T cold over T hot. And the efficiency is also, in general, efficiency is the amount of work that you do divided by QH. And they also tell you that all three engines draw the same amount of heat from the hot reservoir. So this is the same for all three. And now, by just looking at these numbers, I can already guess that engine C will be the most efficient, because compared to engine A, it burns hotter, and compared to engine B, it has a colder cold reservoir for heat damping. So C is, by just looking at this without computing any numbers, I'm guessing that C is the number one. About A and B, I'm not sure. Given the same gap of 100 degrees, would I rather have 400, 500 or 500, 600? Let's find out. So what we do here is we simply compute efficiency for all of them. Efficiency for this one is 1 minus 400 over 500. And for this one, it's 1 minus 500 over 600. And for this one, it's 1 minus 400 over 600. So math in this week will be pretty simple, as long as you know what is it that you need to compute. The computation itself will be pretty simple. So here I have 1 minus 4/5, that's 1/5 of efficiency. Here I have 1 minus 5/6, that's 1/6 of efficiency. And here I have 1 minus 4/6, that's 2/6, that's 1/3. So as we already guessed, this is the most efficient engine at 30% efficiency. Then this engine at 20% efficiency, and then this engine, whatever 1 over 6 is, this is the least efficient. So one thing that I've learned is that if I have the same gap of 100 degrees, I would rather have that gap at a lower temperature than at a higher temperature, because 100 degrees of difference is fractionally more here in this situation compared to this situation. If you are on the surface of a sun where temperature is 6,000, then the difference between 6,000 and 6,100 isn't really a big deal. But if you are at room temperature, which is 270, then the difference between 270 and 370 is really, really a big deal. Now let's look at question number 2 on slide number 7. So in this question, they tell us that there is an inventor who has 4 engine ideas. And for those engines, these are the numbers: QH, QL, work. So 4. For 200 negative 175, 40. This is all in joules. Everything is in joules. For engine B, we have 500, negative 200, and we have 400 joules of work. For engine C, we have 600. We draw 600 joules of energy. We dump 200 joules of energy, and the work is 400. And the final engine has 100 joules of energy drawn. We dump 90 joules of energy, and 10 joules of energy are then used. And these engines operate between temperatures of 300 degrees and 400 degrees. The question is, which laws of thermodynamics do these engines violate? The first law or the second law? Now, I have to remind you what those laws mean, because I don't think we have explicitly talked about them, because it wasn't necessary. The first law of thermodynamics is basically conservation of energy. This is just historic nomenclature. And the second law of thermodynamics, second law, is, so this will sound weird, but at some point when you learn all of the thermodynamics in the future, this will all make sense. The second law is that an engine cannot be more efficient than a Carnot engine. This is one of the statements. There are other ways of stating the second law, but let's go with this statement. So the first law says energy must be conserved. The second law says you cannot have a more efficient energy than Carnot's, more efficient engine than Carnot's engine. So the second law is kind of more restrictive than the first. So let's see how this works for the engines that we have. So the conservation of energy is basically that QH must be equal to QL plus W, where QL is with the plus sign. So let's check the first engine. This first engine fails the first law, because 40 plus 175 is more than 200. So somehow we got more energy out than there was available. The second engine doesn't violate the first law because, oh no, wait, it does violate the first law, the second law, because, sorry, the first law, because 200 plus 400 is more than 500. So this is also not possible. The third engine doesn't violate the first law because energy is conserved, 600, 200, 400. And the last engine also doesn't violate the first law of thermodynamics, because 90 is used, 90 is dumped, and 10 joules is used for work. So we are okay with the conservation of energy. Now let's look at the second law. The second law tells us that engine cannot be more efficient than this. So let's see what that efficiency is. Basically, your efficiency cannot be more than 1 minus 300 over 400 for this specific engine. So for our numbers, this is 1 minus 3/4, this is 1/4, this is 25%. So efficiency, which is also work over drawn heat, cannot be more than 25%. Now for the third engine, the declared efficiency is work over QH, 400 over 600. This is 4/6, 2/3. This is more than 25%. So this engine, even though it satisfies conservation of energy, doesn't satisfy the second law of thermodynamics. But if you check the fourth engine, then its efficiency is 10 over 100. That's 10%. That's less than 25%. So the fourth engine is the only engine that's okay with both the first and the second laws. So this is the only engine that could be a real engine. These three, he probably made some mistaken calculations. So engine D is good with both laws. Engines A, B, and C are not okay with one of the laws, at least one of the laws. Now I will move to problems, and I will start with problem 1 on slide number 8. In this problem, we have a Carnot engine that operates between 320 and 260 kelvins. It absorbs 500 joules. The question is, how much work does it do? So let me first compute the efficiency. Since this is a Carnot engine, I know that the efficiency is 1 minus 260 over 320. And I also know that efficiency is work divided by heat that I use. And so if the heat is 500 joules, then from here I can find my work. And this work is 500 times 1 minus 260 over 320. So I'm not going to compute this number, but this number is obviously less than 500. And exactly what fraction of 500 I use for work will depend on this efficiency. The second question is, if this engine was working in reverse as a refrigerator, how much work would you need to do to remove 1,000 joules of heat from the cold reservoir? So now I have to remember the efficiency, or rather the performance of a refrigerator. For a perfect refrigerator, it's T cold divided by T hot minus T cold. So if this is really a Carnot refrigerator, its coefficient of performance will be 260 over 320 minus 260. This is 260 over 60, 26 over 6, 13 over 3, 4 point something, 4.3. Now, the coefficient of performance is the amount of heat that I remove divided by the amount of work that I have to do. So if this coefficient is 4.3, then to remove 1,000 joules, I would need to do 1,000 divided by 4.3 joules of work. This is roughly, this is slightly less than 250 joules. Which makes sense. My coefficient of performance is about 4, so I need about 4 times less work to remove 1,000 joules of heat from the cold place. Now let's move to the second problem, problem number 2 on slide number 9. This problem is also about a Carnot refrigerator. So a perfect refrigerator. They tell us that it extracts 35 kilojoules of energy. And they tell us that the coefficient of performance is 4.6. And the question is, how much work do you do and how much heat do you dump? So this should also be easy. Let me just remember what the coefficient of performance is. The coefficient of performance is QL divided by W. And I know that this coefficient of performance is 4.6, and I'm removing 35 kilojoules of heat. So I must be doing this much work. Whatever 35 divided by 4.6 is, that's the amount of work that I'm doing every cycle. Now, the next question is, how much heat do I transfer to the room? And to find that, I would have to engage the conservation of energy, or the first law of thermodynamics, that tells me that QH is equal to QL plus W. So this is 35 kilojoules plus 35 divided by 4.6 kilojoules. Whatever this number is, that's the amount of kilojoules of energy, thermal energy, that I dump into the room. So as expected, I put a bit more thermal energy into the room than I removed from the refrigerator. Let's now do the final problem on slide number 10. In this problem, we have a Carnot engine that works at a high temperature of 400 kelvins, has an efficiency of 30%. And the question is, let's say I want to make it 40% efficient. Then if I want to make it 40% efficient, I have to either increase the high temperature or decrease the low temperature. Sometimes it's difficult to increase the high temperature because it's limited by the temperature of what I'm burning. So I could decrease the low temperature. And the question is, by how much should I decrease the low temperature so that the efficiency goes up to 40%? So let's write down the basic equations. Efficiency is, for a Carnot engine, the efficiency is 1 minus T low over T high. Excuse me. And that's 30% apparently. I also know that my high temperature is 400. So from here, I can easily find my low temperature. My low temperature is 1 minus 0.3 times 400. This is 0.7 times 400. This is 280. So the low temperature is 280 kelvins. Okay, now what should it be to make the engine 40% efficient? Let's see, that shouldn't be too hard to compute. So I have the same equation, but over here I have 0.4. And now T low is 1 minus 0.4 times 400, 0.6 times 400, 240 kelvins. Okay, makes sense. So by dropping temperature by 40 degrees, I increase the efficiency of my engine by 10%. So again, as I said, from technical point of view, I don't believe any of the homework problems should be difficult. And the basic concepts are really, really simple. There are 4 equations for efficiencies and performance coefficients, and for Carnot, perfect stuff. But if you run into any problems, feel free to join our Zoom help room on Mondays, Wednesdays, and Fridays. Thank you.